Hey guys, so today we are going to look at series and parallel circuits. We're going to be able to talk about three things when we talk about, well, four things I suppose, when we talk about series and parallel circuits. We're going to be able to talk about the current throughout the circuits in series and in parallel. We're going to look at voltage through series and parallel circuits. We're also going to look at what happens to resistance in series and parallel. Okay, so we're gonna start off with series. I've drawn a small series circuit here with 1, 2, 3 resistors in it. So we've also got a cell at the top here. So when we're talking about the total amounts, first of all, we're going to start off with the current. We're going to write I here, and that is the total current. So we write that the total current we can measure at the top here. Now, we can also measure the current at all these three different stages. So we're going to say current 1 is here, current 2 is here, and current 3 is here. Now, when resistors are connected in series, the current through each resistor is the same. In other words, the current is the same at all points in a series circuit. So what we can say for this is the total current is equal to the current at position 1, it's equal to the current at position 2, and it's equal to the current at position 3. So basically, we could use an ammeter at any point around this circuit, and the current would be the same. It would be the same as it is at the beginning in a series circuit. Now, the next thing we want to talk about is voltage. So again, we're going to say the total voltage is at the cell here. We can talk about voltage 1, we could talk about voltage 2, and we can talk about voltage 3. This is also known as potential difference. They like to use the word potential difference in the exams. I'm using voltage for today because it's a bit simpler and a bit quicker to write down instead of PD. So what we can say about voltage, when resistors are connected in series, the total voltage or potential difference across all the resistors is equal to the sum of the voltages across each resistor. So in other words, the voltages around the circuit add up to the voltage of the supply. So we can write this as voltage total equals the voltage at number 1 plus the voltage at number 2 plus the voltage at number 3. Now we could take out any of these resistors. If we just have 1, it would still be, the voltage would be the same here as it would be total there. If we had 2, we just add V1 and V2. If we had 3 or 4 and so forth. Now, the next important thing is the resistance. So again, we can look at the resistance here, we can look at the resistance here, and we can look at the resistance here. So at each 3 steps, we can have the resistance total here as well. So for this one, the total resistance of a number of resistors in series is equal to the sum of all the individual resistances. So this one's nice and simple actually. So all it is the total resistance of this circuit is this resistance, add this resistance, add this resistance. Really nice and simple. You just add those resistances together. So the series one, really nice. So if we had to work out the resistance at R3, so we didn't know this resistance here, but we knew these 3. All we'd have to do is add these 2 together and take it away from the total. So nice and simple. Resistance is just that one, add that one, add that one. Voltage in series is that one, add that one, add that one, that one, add that one, add that one. And then you've got for the current is I1 is the same as the total. So current is always conserved around the circuit. Okay, so carrying on now, we're moving on to parallel circuits. So we're going to look at exactly the same things again. We're going to look at current, voltage and resistance, but this time in a parallel circuit. You can see it's parallel now because these branches of the circuit are running parallel to each other. Nice and easy. So to remember that one, hopefully. So what we've got, we're going to start off again with, we can find the total current here. We're going to talk about the total current being at the cell. We're also going to, and then we're going to have the current over resistor 1. We're going to have the current over resistor 2, and we're going to have the current, the flow of electrons, at resistor 3. We're also going to be able to talk about the voltage, the total voltage, we measure that here, over the cell. We're going to talk about the voltage at resistor 1, the voltage at resistor 2, the voltage at resistor 3. I mean, we could use any number of resistors, and this would, any number of multiple resistors in parallel, and this would still reply. I've just chosen to use 3. And then finally, we're going to talk about resistance, the total resistance. Now, that's slightly more complicated for this one. So first of all, we'll start off with resistors in parallel. So when resistors are connected in parallel, the supply current, this one here, the total current is equal to the sum of the currents through each resistor. So nice, simple, slightly different to the series one. The series one, we had, they were equal all through, but this time it's total current equals resistor 1, current 1 plus current 2 plus current 3. So we add the currents together that are at each point along this, around this circuit. We could do that using an ammeter to measure current. Now the next thing, that's nice and simple. It's just we need to remember that for parallel, that you add them together, the current together, to get the total. For the series, it's equal everywhere. Now, when resistors are connected in parallel, they have the same potential difference across them. Any components in parallel have the same potential difference across them. So therefore, for voltage, we've got the total voltage is always the same at any position. So voltage 1, total voltage, is the same as the voltage at 1, is the same as the voltage at 2, and is the same as the voltage at 3. So the total voltage and all voltages, potential differences across these parallel branches is the same. Now, if we're talking about resistance, this is where it gets slightly more complicated. So in order to calculate the total resistance of two resistors connected in parallel, we use this equation. And this is 1 over resistance equals 1 over resistor 1 plus 1 over resistor 2. Now what this means is that if we wanted to calculate the resistance around the circuit, we'd need to use this equation. We can use this for the third resistor as well. So what we need to do to calculate this is we need to do 1 divided by the resistance at number 1, add 1 divided by the resistance at number 2, add 1 divided by the resistance of resistor 3. To calculate the total resistance of 3 resistors connected in parallel, and we've added a third one to this. So we've got our third resistor here. We could use this for our first and second resistor, just for these 2 resistors, but we've got a third resistor in our circuit, so we're going to use that. So this is how we calculate the resistance of the circuit, of a parallel circuit, the voltage, the potential difference of a parallel circuit, and the current of a parallel circuit.